Welcome to our Lesson 4 lecture. Lesson 4 is all about the gradient. We're going to start today by talking about partial derivatives and different ways of writing those partial derivatives. So you can see on the top line there, I have 5 different ways of writing the partial derivative of a function with respect to x. And the second line there, I have partial derivative of a function with respect to y. Okay. One thing I do want to point out to you, just so you know, that these middle ones here, those are f and then subscript x or subscript y. It may not look like that from the way I wrote it, but it's supposed to be a subscript x or a subscript y. All right, so some quick basic examples here. The first one says find the partial derivative of that function with respect to x, which means that y is essentially a constant. Okay, so we'll have to use the product rule here for this. So we have the first function times the derivative of the second function. So the derivative of an e exponential, remember, is the function itself. And then using the chain rule, and then the chain rule again, plus the second function times the derivative of the first function, which is just 1. Okay, we can do a little simplifying with that. You know, from your BC class, it's never a good idea to leave negative exponents in there. So if we wanted to simplify this down, we can get that expression there. So that would be our partial derivative of that function with respect to x. And for b, we're taking the partial derivative of that function with respect to y. So anything that's not y is going to be treated like a constant here. Again, we're using the chain rule. So derivative of sine is cosine. The inside function does not change here. And times the derivative of the inside function. Remember, this is with respect to y, so the x is treated like a constant, and the y is our variable there. So that'd be it. Let's talk about the gradient now. The gradient is a vector which points in the direction of greatest initial increase. All right, there's your formula for a 3-dimensional gradient. Obviously, if it's 2-dimensional, basically you would just get rid of this third part here. But for a 3-dimensional gradient, you'd use that formula there. The partial derivative of the function with respect to x, partial derivative of the function with respect to y, partial derivative of the function with respect to z. So let's take a look at this first one here. This is just a 2-dimensional one. Gradient, we use an upside-down delta for that, upside-down triangle. So gradient of f, the derivative of that function with respect to x is 1 plus 0, so just 1. And the derivative of that function with respect to y is 0 plus e to the y, or just e to the y. Right here we have a 3-dimensional gradient. So the derivative of this function with respect to x first, so cosine z is essentially treated as a constant here. So we have cosine z times the derivative of xy, which in this case is y, times e to the xy. So we can write that as y cosine z e to the xy. And then the derivative of this function with respect to y is basically the same, except we have an x out in front. And then the derivative of this function with respect to z. So we're going to take the derivative of basically just cosine z, which is negative sine z. So it's negative sine z, and the e is treated like a constant in this part. And there's your gradient with respect to in 3 dimensions there. Sorry. Okay, finding local mins and maxes and also saddle points. The local extrema of a function occur when the gradient is 0, 0, or 0, 0, 0. However, it's important to note that each point where the gradient is the 0 vector is only a possible candidate for a local min or max. Okay? So you see in the first picture there, the gradient would be 0 at that point, but it is not a max or a min. It would be a saddle point. The second picture there, it is an actual minimum. So the second derivative test, first you want to make sure you find where the gradient is equal to 0. And then you want to find the second derivative with respect to x, second partial derivative with respect to x, and the Hessian determinant, which is given by that formula there. If the Hessian is negative, it's automatically a saddle point. No more work. If the Hessian is positive, you have to make sure you find that second partial derivative. And if the second partial derivative is positive, it's a local minimum. If the second partial derivative is negative, you have a local maximum. All right, so let's take a look at an example here. A lot of work for these problems that you're doing by hand. All right, so the first thing we're going to do is take the gradient and set it equal to 0. So there's my gradients. So we're going to set this equal to zero, 0. So the first part, 2x e to the negative y, will only be 0 at one point, at one value. And that's when x would be equal to 0. Okay, there's nothing we could put in for y to make that 0. So only when x is 0 will that first part be 0. The second part, let's factor out a positive e to the negative y. And we're left with negative y squared plus 2y minus x squared. That first part, again, will never be 0. We can't make that negative e to the y ever 0. But maybe we can do the second part. I'm just going to rewrite it a little bit here. All right, we already see that x has to be 0. So if we put 0 in for x, and if we factor this, we get 2 answers. So we have 2 candidates for possible extrema. 0, 0, and 0, 2. So those could be maximums, these could be minimums, those could be saddle points. Our next job is to figure that out. So let's find the Hessian determinant of that. So our Hessian, that's subscript 0, 0 there. Sorry for the bad handwriting there. We're going to have to find that. So what we're going to do is we're going to take the second partial derivative. The partial derivative of 2x e to the negative y with respect to x is just 2e to the negative y. The second partial derivative of y with respect to y there. We'll have to do some work. This is a couple different product rules. Sorry for the squishy writing there. And then the second partial derivative of f of x with respect to y would be just that, because there's only the one term all the way over here that has an x in it. Okay, so now our Hessian. At 0, 0 would be 4. The second partial derivative of x with respect to x there, if you put 0 in for y, really, you just get 2 back. So our Hessian is positive. Our second partial derivative is positive. That tells us that 0, 0 has a relative min. So 0, 0, comma f of 0, 0. 0, 0, f of 0, 0 is a relative min. And, just like you did in BC, explain why. Hessian is positive, and second partial derivative with respect to x is also positive. Okay, and then we're going to do the same thing here at 0, 2. I'm not going to go through all the work for that. You can do that on your own, but the numeric answer you get is this, which is obviously negative. So you don't really need to go through the process of checking the second partial derivative. As soon as the Hessian is negative, you know that this point is a saddle point, because the Hessian is negative. All right, a lot of work to do on problems like that by hand. Nothing that's too difficult, but just a lot of work in general. The other big part of this chapter is called Lagrange multipliers. So we're trying to maximize or minimize some type of function that's subject to some other function's constraint. All right, so here we're trying to maximize the function f of xy equals x plus 2y, but we're constraining it so that g of xy, x squared plus y over 4 squared, is equal to 1. Okay, you might recognize that second shape as an ellipse, and we're trying to maximize the function subject to its constraint to that ellipse. Okay, so Lagrange multipliers, what you're going to do is you're going to end up setting up a system of equations. What you'll do for the first equation, you'll set the gradient of f equal to some multiplier. That's why it's called Lagrange multipliers. S times the gradient of g. And then you'll set the second function equal to its restraint. And basically we'll end up with a system of equations. Okay, so let's start by finding our two gradients. So the gradient of f is just 1, 2. The gradient of g is 2x, and then you can think of that as y squared over 16, so it would be 2y over 16 or y over 8. So those are two Lagrange multipliers. All right, so we'll set up our two systems of two equations here. Our first one is going to be f's gradient is equal to some multiplier times g's gradient. Okay, and then the second one is just that g of xy is equal to 1. Okay, let's do a little work here with this one first. So first of all, 1 is equal to s times 2x. And then 2 is equal to s times y over 8. All right, so what I'm going to do here is we want to solve this for one of the variables. It doesn't really matter which one you choose. I'm going to try to solve this first one for x. And I'm going to solve the second one so divide that by s for y. So x equals 1 over 2s, and y equals 16 over s. All right, and then we're going to take that second equation that we have, so g of x, y is equal to 1, and we're going to substitute that x and y in for that. So x is going to become 1 over 2s y is going to become 16 over s, so it's going to be 16 over 4s. Doing some simplifying here, we get 1 over 4s squared plus 16 over, 256 over 16s squared, which simplifies down to 16 over s squared equals 1. And it's doing some solving here, so multiplying through by s squared. We get our two possibilities for s. Okay? So now what we can do is we can take those two possibilities for s and we can put them back into x and y. So x is going to be 1 over 2 times plus or minus root 65 over 2, which is just going to be plus or minus 1 over root 65. And then y will be 16 over plus or minus root 65 over 2, which we can simplify down to plus or minus 32 over root 65. And at that point, basically what we just got to do is we got to put those points in and see what we get back. All right? So if we put in this point, again, you can go through the work of putting that into f. It's just x plus 2y, right? So it'd be 1 over root 65 plus 2y, so 32 over root 65. We get 1 plus 64 over 65, so 65 over root 65. Which if you rationalize that, you end up with just root 65. Not that you need to rationalize that, but it looks a whole lot cleaner. So if we put the two positives in there, we get root 65 back. And then if we were to put this point in, I'm not going to go through all the work of that. Again, you get the same answer, but negative. So it would be negative root 65. So the question says we're trying to maximize it. Our two possible values are root 65 or negative root 65. Clearly, root 65 is bigger. So we would say that f has a max of positive root 65 when x equals this, and y equals this. All right, maximizers and minimizers. A function has no maximizer if it increases without bound, meaning that the value of the function would approach infinity. Okay? So a function has no minimizer if it decreases without bound, meaning it would approach negative infinity. Okay? So here's a quick example here. Does this function have a maximizer or a minimizer? You could look at that, and obviously it does have a maximum. You should be able to tell that by looking at the function here. If we make the denominator as small as we possibly can, then the function would have a maximum, okay? So what values would give you that? We want to know basically if the denominator was as small as it can be. Because the second and third terms there are squared, we want those to be 0. And if that was true, the denominator would be 1. All right, so how do we figure out what that would be? Well, x could be 1. X would have to be 1, or for that second part to be 0. And if x is 1, you get 2 times 1 minus y equals 0. So y would have to be 2. If those two were true, the denominator would then be 1, which means the maximum value would be 100. Okay, does this function have a minimizer? It would not have a minimizer. Okay, why not? Because the denominator could get bigger and bigger and bigger, which makes this function smaller and smaller and smaller as it approaches 0. Okay, it would never actually reach 0, but it would get closer and closer and closer to 0 as the denominator got bigger and bigger. All right, so the last thing that we're going to talk about here is the total differential. It's pretty much the gradient, except it's not a vector, it's an actual number. So what you're going to do is you're going to take the 3 partial derivatives and add them together. All right, so an example here, the total differential for this function here. So the derivative of this function with respect to x would be y z dx. With respect to y would be x z dy. And with respect to z would be x y dz. And that is your total differential. Suppose the graph of z, which is represented there, represents a terrain featuring 2 peaks and 2 pits. I don't know if you could see it all in that picture, but there's a pit behind that first mountain there. With all distances measured in miles, z is the altitude above the point at sea level in the xy plane. For instance, the height of the picture point P is at z of -1,1, approximately 0.2489 miles. We ask at what rate we climb if, starting at the point P, we had either due east or due north. So what we would do is we'd find the partial derivatives of that. So let's do north first. So then north basically means we would take the derivative, the partial derivative with respect to y. Okay, so this would be a product rule and a chain rule. All right, we can substitute in our x's and our y's that we know, which is -1 for x and +1 for y. And if we simplify that down, doing some quick calculations here, that should get us down to 15 over e cubed. 15 over e cubed. Okay? So what does that mean? That means we would be climbing up. We would be climbing up at a rate of 15 over e cubed if we headed north from that point. If we headed straight north from that point, we'd be climbing up at that rate. And we can repeat that process for east. So for east, obviously, we're going to be heading in the x direction. So it's very similar partial derivative. Except this time we're multiplying by -2x instead of -4y. And 5y here instead of 5x. But the rest of it's pretty much the same. All right, and again, if we substitute in, I'm not going to go through all the work for that, but if we substitute in the -1, 1 there, we would get 5 over e cubed, which means we'd be climbing down at a rate of positive 5 over e cubed. Okay, the negative out in front just means that we'd be climbing down. The hill would be pointing down in that direction, that's all. All right, so that's it. That's a lot here for lesson 4, I know. But that'll do it for this lecture. If you have questions, as always, you can just let me know.